Hi, my name is Stephan Weiss, and I'd like to welcome you to this first MHCI 2020 keynote on mathematical tools for processing broadband multi-sensor signals. The context to this conference might be that if you have human-computer interfaces that often involves, for example, microphone arrays or loudspeaker arrays, and these are inherently broadband signals that span several octaves. What I'd like to do in this presentation is to present you a tool that I and a few colleagues have been working on. This tool involves polynomial matrices, so I will talk a little bit about what polynomial matrices are, where you come across those, and some of the basic properties and operations that involve these polynomial matrices. In order to formulate and solve broadband multi-sensor problems, we need a factorization similar to what you know as a standard linear algebraic tool such as the eigenvalue or singular value decomposition. So the second part of this talk will be focused on decompositions of a particular type of polynomial matrix that we encounter in a lot of these problems. And finally, I'll give you an example from broadband beamforming. This is a bit simplified from the paper that accompanies this keynote, and I hope that you find this useful and perhaps stimulating in order to solve some of the broadband multi-sensor problems that you have here in your own research. So to start, a polynomial matrix is basically a matrix that is not constant, containing real or complex valued entries. It's a matrix that contains functions, and you could write this as a matrix polynomial. So as a polynomial, for example, in Z that has matrix valued coefficients, or you could write this as a matrix that contains functions as entries. So in this case, you have a 2x2 matrix, and each of these entries is a function in Z. The two are equivalent for the simple polynomial case. If you have rational functions, then we usually stick with this equation 2, where you have functions inside a matrix. So where can we encounter this? If you, for example, come from the communication side, then you often have to deal with multiple input, multiple output systems. So we have here two transmitters, X1 and X2, and two receive signals, Y1 and Y2. And each of the channels that connects a pair of transmitting receivers will have an impulse response. So these impulse responses, for example, are H11 of n. And what you then have is a channel matrix that contains impulse responses and not just real or complex valued gain factors. So if you now imagine this, if you had a 2x2 matrix, then every matrix entry is an FIR filter in this case. And if you take a set transform of this, we have a 2x2 matrix that now contains transfer functions. And this is your first polynomial matrix here. If you, for example, deal with filter banks for audio or video coding, then typically you decompose a signal through a series of low pass and band pass filters into different frequency bands. And because of the band limitations, you can decimate or subsample these signals. So this is an analysis filter bank, and you could equivalently write the structure that you have on top as a so-called polyphase implementation, whereby first you demultiplex the signal and then send these demultiplexed components through what's called a polyphase network. So through a matrix of transfer functions, and each of these transfer functions somehow relates to the transfer functions of the filters that you have in the diagram on top. There's a dual operation to this, which is called the synthesis filter bank. So if you have decomposed the signal into its constituent subband signals, you can restore approximately, or ideally perfectly, the original signal by first restoring the original sampling rate through upsampling, and then through interpolation filtering. And again, you can bring this into a polyphase notation, whereby first you send your subband signals through a polyphase network, or what's called a polyphase synthesis matrix, and then you multiplex these signals back together again. So if you now think of this filter bank as something that's back to front. So we first go through the analysis and then through the synthesis filter bank. So for the system to be perfectly reconstructing means that the operation in the middle here has to multiply out to an identity. Yeah. Then basically the demultiplexing and multiplexing operations that occur at the ends of the operation here become transparent. So what we want is that we have these two matrices multiply out to an identity, and it essentially means if you're, for example, given our polyphase analysis matrix, then the polyphase synthesis matrix has to be the inverse of this polyphase analysis matrix. Now, you know how to invert a constant matrix. There's techniques to do that. You can go into MATLAB. The question is, what do you have to do if you deal with a polynomial matrix in this case? Another case where you encounter this in statistics. So if you, for example, want to describe the second order statistics of signals. So the signals that we have come from several sensors, and we have m sensors in total. So each sensor's signal here is placed in a vector. And we can now write what's called a space-time covariance matrix, which basically relates the similarity between these different signals here. And what we need to include is a lag component in order to compare signals in different channels at different times. So if we formulate the space-time covariance matrix, then we end up with a matrix that now depends on this lag component tau. And every element, for example, for m equals 2 here, is going to be an auto or cross-correlation function. So on the main diagonal of our matrix, we have two autocorrelation functions, and in the off diagonals we have cross-correlation functions. So to give you an example for this, so we have here this 2 by 2 matrix. The autocorrelation functions on the main diagonal you see are symmetric for the real valued case, and the cross-correlation functions will also be symmetric to some extent, in the sense that the one here at the lower left-hand corner is the time-reversed complex conjugated copy of the right top corner element here. So this space-time covariance matrix has a particular symmetry. And again, we could now apply a set transform to the space-time covariance matrix, and we get a polynomial matrix R of Z. So at this point, we define a few operations for our polynomial matrices. There's something called a Parahermitian operator, which is an extension of the transposition or Hermitian transpose. And in addition to the Hermitian transpose, which applies a transposition in complex conjugation, this Parahermitian operator, superscript p, additionally applies a time reversal. So on the main diagonal here, we have a function here, or an impulse response, and you see after this Parahermitian operation, this is now time reversed. If we have a component here at the bottom left-hand corner of our matrix, then after Parahermitian transposition, it will appear at the top right-hand corner and be time reversed as well. So this is important because our space-time covariance matrix now fulfills something called a Parahermitian property. And a Parahermitian matrix is a polynomial matrix that has this internal symmetry. So on the main diagonal, we have essentially symmetric components, and in the off diagonals, basically the matrix here is identical to its Hermitian transposed and time reversed version. Okay, so one more operation, and this is what's called a paraunitary matrix. So paraunitary is the extension of what you know as an orthonormal or unitary matrix for constant matrices. And basically, what you know from a unitary matrix, that, for example, A multiplied with its Hermitian transpose is an identity. And similarly for a polynomial matrix, if you have a matrix A of Z, and in case this is a paraunitary matrix, then by multiplying it with its Parahermitian transpose, we obtain an identity. Now, if you recall, previously we looked into the design of filter banks, and the polyphase synthesis matrix was the inverse of the polyphase analysis matrix. So for example, now if we create this polyphase synthesis matrix as a paraunitary matrix, then this inversion is dead simple. We also call this paraunitary matrix a lossless property, so it implements a lossless filter bank, and that is an extension again of what we know from a unitary matrix. For example, a unitary matrix only performs a rotation of vectors but does not change the length or the energy content of a vector. So, just as a last item on this first segment, I would like you to demonstrate now that when we operate with these polynomial matrices, things are quite different from the constant matrix case. So for example, if you wanted to invert a system, traditionally we would do this maybe by Gaussian elimination. So we would bring our matrix into an upper right triangular form and then perform a back substitution. So we have here a system of equations whereby A is our matrix, X might be the unknowns, and we have a right-hand side vector as well. So for the first step, we try to eliminate this bottom left-hand element of our matrix. So we perform some modifications to our second equation. And at this point, we actually introduce rational functions. Yeah? So we have to divide by polynomials, and this creates rational functions, increases the order of our system. And if we have a larger matrix where you have to basically repeat these operation steps, then all of a sudden, with every step that we perform in terms of operations, we increase the order of our system. Now that we have seen how operations can increase the order of polynomials, I'd like to discuss one particular approach, one particular application that we require in order to describe and solve many of our broadband problems. And this has got to do with the diagonalization of a space-time covariance matrix, or generally a matrix that satisfies the Parahermitian property. So what we want to do is we want to diagonalize this matrix so that our space-time covariance or cross-spectral density matrix R of Z becomes this product of a diagonal Parahermitian matrix containing eigenvalues. And you see an example below. So on the left-hand side here we have our space-time covariance matrix. On the right-hand side we now have a strongly decorrelated matrix, and that means all the off-diagonal components are 0. The on-diagonal components will still have a polynomial shape or Laurent polynomial shape, so they're not just constants, they're still functions as such. The second part of this factorization is this matrix Q, and this should be a lossless matrix or a paraunitary matrix as we have just introduced it. We've also seen that in order to restrict the growth of the order of these terms, we really would like to approximate this by something that is of low polynomial order and therefore has advantages for an implementation. So first of all, we need to address the theory, and this is this Parahermitian matrix eigenvalue decomposition. So we know now that in most cases, except where we deal with multiplex data, there exists this factorization that simply extends the narrowband EVD to a polynomial EVD, where we have these paraunitary and Parahermitian diagonal factors on the right-hand side. And if R of Z is analytic, so if the space-time covariance matrix, for example, emerges from a system or from signals that have gone through stable causal components, then R of Z will be analytic and these factors will also be analytic. That means that the time domain complements will decay at least exponentially and therefore can be very nicely approximated by finite order polynomials. So a lot of this is based on the work of Franz Rellich from 1937, who performed this for matrices that depend on a real valued parameter, so not necessarily on angular frequency that is cyclic, but on something that evolves continuously. So from this work, we now know that the factors can be analytic, and there's as I said, certain consequences from this. Even though these factors can be algebraic or transcendental functions, that means they basically decay but are infinite of support and cannot necessarily be represented as rational functions, so they have strange patterns, if you like, or no pattern at all. But they can be approximated to arbitrarily fine accuracy by finite order polynomials. So these approximations are d-hatted quantities, and that matters, for example, now if we have our sensor signals x here in this vector x of n. We do this processing by our paraunitary matrix, and now we have strongly decorrelated signals in this vector y of n. So this could be a preprocessor for broadband blind source separation. It could be a subspace projection, so not all of the components of y of n are important anymore. The signal subspace only occupies a reduced dimension, or we could, for example, perform subband coding on these signals with a coding gain advantage as well. The important aspect here is this Q of n is lossless, and we want to keep the order as low as possible in order to encourage implementations of this. Another important aspect is the uniqueness of these factors. So the eigenvalues will be unique. They will be polynomials or Laurent polynomials themselves, so it will be frequency dependent. The eigenvectors, however, are ambiguous. So as you may know, for example, for a constant matrix, you can find an eigenvector and the corresponding eigenvalue. And if you now multiply the eigenvector with a complex, with a phase term, then this phase term still gives you a valid eigenvector afterwards. So there's a phase ambiguity. And if we take the decomposition from the previous page with Q of Z, lambda, and Q Parahermitian here, then we can introduce a spurious term that multiplies out to an identity. And because we can rearrange the order of diagonal matrices, we can basically rearrange this and now can associate these phase terms phi here with our eigenvector matrices, with these paraunitary matrices. And that means that any valid eigenvector can be multiplied by an arbitrary all-pass filter that modifies the phase, doesn't modify the magnitude, and we still have a valid eigenvector afterwards. There's some more intricate problems if you have an algebraic multiplicity of eigenvalues, but you already realize that there's some ambiguity for these eigenvectors potentially. And in the simplest case, if we delay an eigenvector in the time domain, it's still a valid eigenvector. So this again has an implication on the implementability and the delay that these components produce. So this was recent work. A bit further back, John McWhirter came up with polynomial eigenvalue decomposition. So he postulated that a matrix R of Z can be approximately decomposed into these factors here, where U of Z is again a paraunitary matrix, gamma of Z is a Parahermitian diagonal matrix, but this matrix now satisfies some additional constraints. This matrix is supposed to be spectrally majorized, so if we evaluate these functions on the unit circle, then they have to be ordered. The first function has always the highest value for any type of frequency that you pick. The second function will be the second highest, and so forth. And I'll show you a plot in a moment. So the spectral majorization is kind of inherent in this decomposition that John McWhirter created here, and there was no proof that this decomposition existed. So the type of work that we have done, that I highlighted on the previous slides, puts the foundation underneath that. However, for John McWhirter's algorithm, there's several algorithms for this decomposition. There's several algorithms that can achieve this factorization. So John published this in 2007, and some more papers emerged over the last 1.5 decades. There's two families of algorithms. One is called second-order sequential best rotation, the other one sequential matrix diagonalization. And these are iterative time domain algorithms. They operate on a space-time covariance matrix, and they basically at every step of iteration check for the largest off-diagonal element. With a delay operation, they bring this component onto the lag 0 slice. In the lag 0 slice, you then perform a Givens rotation, and you eliminate this largest off-diagonal element and transfers its energy onto the main diagonal. So these algorithms are proven to converge, and they've been very successful for a number of different applications. We've also looked at algorithms that solve for analytic eigenvalues, and I'd like to indicate to you how that differs from these SBR2 and SMT algorithms. So this is something that we've only recently performed. It's not 2010, it's 2020. I'm sorry for this, I got the decade wrong. So what we do is we don't operate in the time domain, we actually operate in the discrete Fourier domain. And at every frequency bin, we evaluate an EVD, and for example, for the eigenvalues in every frequency bin, we now get an evaluation. The difficulty now is everything about these broadband processing methods exploit the fact that by processing the time domain, we preserve the spectral coherence of broadband signals. Now, by operating the DFT domain, we basically lose this glue that we have between the different DFT components, and what we need to do is we need now to find an association between these different frequency bins such that the functions that we associate through this are maximally smooth. And I'll give you two examples below. So the first association would be a spectrally majorized one. So at every frequency bin, we always assign the higher value to the blue function and the lower value to the red function. But we could also try to weave maximally smooth functions through this. And analytic functions are infinitely differentiable. So what we can do is we can basically interpolate through these points, determine a particular derivative, and then check the power in this derivative. And if it's not an analytic function, then the power in these derivatives can become quite large. So there's an algorithm now that basically extracts these analytic rather than spectrally majorized eigenvalues as well. So I'll give you an example for this. We start off from a ground truth space-time covariance matrix. So we have two eigenvalues here of order 2, and we have some a paraunitary matrix here as well. In total, this will create a space-time covariance matrix for us. So the analytic solution to this are the type of eigenvalues that you've seen before. In the top diagram, we evaluate now in the unit circle, and you see you have these two periodic smooth eigenvalues that basically raise sine and cosine functions. Yeah, they have the time domain support of 2. And for the eigenvectors, we actually look as a metric towards the subspace angle between the first eigenvector at DC for the first component, and then take the angle to any subsequent frequency evaluation. And what you see here as well, we basically have a smooth progression of the subspace angle, and because it's a Hermitian angle and we take the modulus, these are actually not discontinuities in the subspace, these are smooth as well. Yeah, so this is now an expression of the smoothness of the eigenvectors. So these are the type of quantities we can extract with these new type of algorithms. If we look for the spectrally majorized solution, then we could start with the analytic solution, and we basically snip at these algebraic multiplicities. So we have these two switching points here. We create now a spectrally majorized function for the eigenvalues. The problem is this function is no longer differentiable, and if you try to approximate a non-differentiable function, suddenly you require quite a high order. It's not an absolutely convergent function in the time domain anymore. And even worse for the eigenvectors, if we perform a permutation here as well, we actually end up with discontinuities in these subspace angles. Yeah, because eigenvectors are inherently orthogonal to each other. If you switch there, you have a discontinuity, and again the approximation order to approximate a discontinuous function can be quite high. So this is now the solution that SBR2 or SMD, for example, provide. We used SBR2 in this case. So the eigenvalues you see are spectrally majorized, of course, because we perform a polynomial approximation. This non-differentiability is not particularly sharp, so it has to be a smooth transition. And for the eigenvectors, you can actually see how the subspace angles refer to what we analyzed before. And you can now see these switching points as well. And of course, because we're trying to approximate a discontinuity, you see these Gibbs phenomena appearing. The key is now that for the true solution, for the analytic eigenvalues, we needed an order for the eigenvalues of 2 and a similarly low order for the eigenvectors. If you now do a spectrally majorized decomposition and approximate those eigenvalues and eigenvectors, then the order will be much higher. So as I emphasized before, the order of these decompositions can be quite important if you try to create a feasible technical solution that you can implement on a processor. Therefore, this really matters. In this last segment, I would like to give you an example of how we can apply these polynomial matrix techniques to address a broadband beamformer design. Our beamformer is based on M sensors that are illuminated by a signal S of n from a particular angle of arrival. And this angle of arrival implies that our signal will now arrive with different time delays at the different sensor elements. As a result, our received data vector x will contain S of n with different time delays, or we can represent this as a convolution between our source signal S of n and a vector of fractional delay filters, each implementing a delay tau. In the Z domain, this vector of fractional delay filters becomes what's called a broadband steering vector. And if we evaluated this broadband steering vector at a particular frequency, i.e. if we go from the broadband case back to the narrowband case, then we simply obtain a vector of phase shifts. So these time delays are now reduced to phase shifts, which are in the narrowband case sufficient to characterize the angle of arrival. If we wanted to solve the narrowband beamformer, then this phase shift can be corrected by complex multipliers, and we only need to follow every sensor element with a complex multiplier, W1, W2, and so forth. So to design these coefficients, we need to formulate a problem. Here we want to solve this in the sense of a minimum variance distortionless response beamformer. That means we want to minimize the output power. As a trivial solution, minimizing E of n would simply imply that we set our coefficients to 0. So in order to avoid this, we need to protect our signal of interest by a constraint. So you see the problem formulation here in equations 19 and 20. These are based on the previous definition of our space-time covariance matrix, but since we have a narrowband problem, we only need the zero lag component of that space-time covariance matrix, and the output power is now given by a function of these filter coefficients W and our instantaneous space-time covariance matrix R of 0. The constraint that we require now uses this narrowband steering vector that I mentioned before, containing phase shifts, which we multiply against our weight vector W. And this inner product should have a value of 1. So this gives us the distortionless response part of the MVDR problem. If we were to go to the broadband case, then using a complex multiplier after each sensor is insufficient, and we need to operate with tap delay lines, in this case tap delay lines of length L. That means in order to formulate our output, we can again take an inner product between the weight vector, which is now m times L coefficients long, and similarly we define a data vector which is also length m times L, which contains the m sensors but also the L differently delayed versions of our different signals here. So if we now want to formulate a broadband beamformer problem, that's a bit more complicated than the narrowband case. So particularly constraints can be quite challenging because the constraint now needs to be enforced over the entire range of frequencies. Typically what we do is that we we impose point constraints at particular frequencies omega 0, omega 1 and so forth, and dot these along the frequency axis. So we have in total maybe L or more constraints in order to preserve our signal of interest, and this gives us then our constraint equation in equation 22. Yeah, but this is not a single constraint anymore. C is now a matrix and contains a number of equations to enforce these constraints. One way to solve the MVDR problem, i.e. to solve an constraint optimization problem, is by means of a generalized side-lobe canceller. So the power of this technique is to convert this constraint optimization problem to an unconstrained one, and that works in two steps. The first step is the upper path of the diagram that you see at the bottom. We have what's called a quiescent beamformer V sub Q here. And this beamformer is derived from the constraints and simply extracts the signal of interest plus any components that might be in the environment as well. And it tries to suppress these as best as possible based on omnidirectional noise. However, specific interferers are not particularly strongly attenuated, and in order to suppress these, we need a second part to our processor here, which is the bottom part of the GSC structure. So down there we have what's called the blocking matrix B, and the blocking matrix eliminates the signal of interest, so it's orthogonal to the quiescent vector WQ. So at the output of this blocking matrix, the signal U of n contains the interference and the jammers, etc. in the environment, but no longer contains any handle on our signal of interest. And the rest is now a classical noise cancellation problem. So we have an adaptive processor VA here, which basically reshapes the noise and interference such that we can cancel this from the output of our quiescent beamformer, such that E of n now only contains the signal of interest ideally. So this is the standard broadband beamformer in this case, which is now based on the dimension m, the number of sensors, and the dimension L for our tap delay line length. If we go to the polynomial case, then we can perhaps remember how we solved this in the narrowband case. So we can again formulate a constraint problem. We can formulate the output power minimization. So we can base this again on a vector of filter coefficients, the spacetime covariance matrix as well. And for the constraints, we now have a single polynomial equation that involves our broadband steering vector A here, our coefficient vector W, and if we wanted to have a distortionless response, then the target function f of z would be unity in this case. Just to give you an idea of how accurate these broadband steering vectors are, because fractional delay filters are hard to implement, particularly towards half the sampling rate. So the accuracy of these is pretty good. So the metric that we apply over frequency is basically how well they satisfy an orthonormality. So for most frequencies, the orthonormality is decent enough, and the performance only breaks down towards half the sampling rate. So with this, we can now formulate a polynomial generalized side-lobe canceller. So we simply, where we previously for the narrowband case had matrices and vectors, we introduced their polynomial equivalence. We have a quiescent beamformer that is derived from the constraint equation. In the accompanying paper, you find something that has a slightly more complicated constraint equation, so also includes jamming directions, etc. In our case, the design of this WQ is quite simple. It's simply the broadband steering vector or the matched filter to this. But the blocking matrix now is a little more intricate. So this blocking matrix has to be orthogonal to the quiescent vector, and we can formulate this via a paraunitary matrix completion. So using these polynomial eigenvalue decomposition algorithms that I've introduced in the previous section, from WQ we can actually derive this blocking matrix B of Z such that it suppresses the signal of interest sufficiently well. By sufficiently well, I mean we deal with polynomial approximations, and I give you an indication of this in a moment. Thereafter, we operate our standard noise canceller with an adaptive processor W sub A here. So this is the basically the consideration for the distortion that the blocking matrix introduces. The blocking matrix has to remove the signal of interest. This shows the maximum components that leak through this matrix with respect to our signal at every frequency. So this gives you an indication of how accurate this matrix is going to be. So the fact that it's not perfect is because we have a polynomial approximation again towards half the sampling rate. The performance starts to break down a bit more. But in general, this will be sufficient here. If it wasn't sufficient, the generalized sidelobe canceller tends to cancel the signal as well as the interference. So that is a concern. Now, as a first step, I'll just look at the computational complexity of these techniques. For our standard broadband beamformer, all the three components, the Quiescent Beamformer, blocking matrix, and adaptive part, are derived from the number of sensors M and the adaptive delay line length L. For our polynomial approach, the dimension of the Quiescent beamformer depends on the accuracy that we select for the broadband steering vectors, and we would perform a truncation on our blocking matrix to satisfy a sufficient polynomial approximation as well. So these two quantities are T and N. And you see that in this table that you have on the slide, the major cost in implementing the system is actually the blocking matrix, which in the standard case is m squared of the order of m squared times L squared, whereas for the polynomial case we have m squared times n. So if n is sufficiently lower than L squared, then we have a significant computational advantage here. So to give you a numerical example now, we operate with an array of 8 sensors, and in our environment we assume 4 sources. We have a signal of interest towards 30 degrees. So in this diagram you see over the angle of arrival on the horizontal axis the frequency range over which these sources are active. So our signal of interest in blue comes from 30 degrees, is active over the entire frequency range, and we have 3 bandpass interferers that we would like to cancel. These interferers are 40 dB above in strength, above the signal of interest. The parameters that we choose for this system here is an adaptive filter length of 175, and it suffices here to choose a fractional delay filter of 50, and the blocking matrix was truncated to 40 coefficients. As a result of this, we can already derive the computational complexity, which for the polynomial beamformer is 2 orders of magnitude below the cost of the standard beamformer. So that is significantly less in this case. Now, in terms of the performance, if you just look at the Quiescent beamformer, which preserves the signal of interest in look direction, but doesn't impose any particular constraints, this is the directivity pattern, meaning the gain response of our beamformer with respect to, on the horizontal axis, angle of arrival, and in the depth axis, frequency, is the same for essentially the same for the proposed and the standard beamformer. What you see here as well is a characteristic of broadband beamforming. The resolution of the beamformer is frequency dependent. So at DC we have no distinction with respect to angle of arrival. The highest resolution that we can get is towards the high end of the frequency range. If we now adapt the beamformer, that means we perform noise cancellation and target now the interferers as well, then you see the directivity pattern of the overall beamformer here for the proposed solution using the polynomial matrix approach. So we still enforce our gain of 1 in the direction of arrival, but we have also imposed notches now with respect to the interference directions at 80, -10, and -40 degrees. And the situation for the standard beamformer is very similar. We also impose the same notches or the same nulls for the interferers, but you see that the ripple structure here in the look direction of the beamformer is a bit different to what we had for our proposed solution. So I'll focus a bit on this now, and basically we look now in look direction 30 degrees across frequency, and we check how well our gain of 1 is preserved. So whether our beamformer is indeed a distortionless response beamformer. So what you have here along the horizontal axis is the normalized angular frequency from 0 up to half the sampling rate. Remember, at half sampling rate, the fractional delay filters start to break down in performance. Our red curves here are for the polynomial approach, so they're fairly accurate, quite close to 0 dB or a gain of 1. The standard beamformers start to oscillate quite a lot once we have adapted the beamformer. And this basically means that if you look here, the black stars in this response are the places where we tie down this response using point constraints in the Fourier domain. So these constraints are satisfied, but we basically get oscillations in between. And we don't have a particularly flat response with respect to our signal of interest. So to summarize, in this keynote, I've hopefully warmed you a little bit towards solutions for broadband multi-sensor problems using polynomial matrices. Particularly, we've looked at matrix factorizations that evolve around the space-time covariance matrix, which satisfies this Parahermitian property. And as an example, I've shown you the design of a broadband beamformer, which offers a lower complexity to the standard broadband approach and has computational advantages in terms of the gain in look direction and the better preservation of the constraints as well. If you're interested to apply this to some of your own problems for broadband multi-sensor applications, then please feel free to try out some of these algorithms which are available from our PhEVD toolbox at the address below. Thank you very much.